Hey everybody, I'm Bill Kinney and this is my Real Analysis Exam 1 Review Problems and Solutions video. If you're looking for some introductory lectures about real analysis, I would encourage you to check out my playlist in the description below. In this video we're going to go through a bunch of foundational definitions, theorem statements, true-false questions, and a bunch of proofs related to the basics of real analysis, for example, that you could find in the first couple chapters of this book by Russell Gordon. It's only later in the semester that we're going to get into heavier duty content about topology and metric spaces, for example, like you can find in Chapter 2 of Baby Rudin. So we're going to start with some definitions here. Let S be a non-empty set of real numbers that is bounded above. So on the real number line, there's some upper bound for S. There's some number, call it capital M, say, perhaps really big, such that every element of S is less than or equal to m, to the left of m on the number line. Part A says define what it means for a real number beta to be the supremum of this non-empty set of real numbers that is bounded above. Part B says state the foundational completeness axiom of the real numbers R. Okay? As far as this definition goes, yes, it's something you can memorize, but you want to think about these things in such a way that it makes sense and that you can reason out the definition if you need to. With the supremum of a set, it's nice to think of it in terms of its other name. It's also called a least upper bound of S. Least upper bound of S, because that essentially describes its two main properties. We're going to go ahead and write beta to be the supremum of S, written sup S. What does this mean? It means two things. Beta is an upper bound of S, and it's the least upper bound of S, but we should really tease out what that means specifically, precisely. This means to be an upper bound of S means that if X is an arbitrary element of S, that implies that X is less than or equal to beta. X being an arbitrary element of S, any element of S, is enough to say, to guarantee that X must be less than or equal to beta. Beta is an upper bound of S. You could also write this with a universal quantifier. You could say X is less than or equal to beta for all X in S. That upside down A means for all. If you're not familiar with this, this means is an element of or is in the set S. Second property is that it's the least upper bound. Not only is it an upper bound of S, but the least upper bound, meaning any other number less than beta is not an upper bound of S. So if alpha is some number less than beta, that implies, in words, alpha is not an upper bound of S. But what does that mean? That means there's some element of S bigger than alpha. There exists, backwards E means there exists, some element x of S such that, st is my abbreviation for such that, alpha is less than x. That means alpha is not an upper bound of S. There's something in S, not necessarily all elements of S, but there's at least one element of S that is bigger than alpha. Okay? So that's what the definition of a supremum is. What is the statement of the completeness axiom? This is part A here. Part B, the completeness axiom says that every non-empty set of real numbers which is bounded above has a supremum that is also a real number. Every non-empty set of real numbers, I could write S is a subset of this blackboard bold R, which is bounded above. There's some number, call it capital M, that is an upper bound for S. You could just say has a supremum, but it's really good to emphasize that it has a supremum which is a real number, or is in R. And it's good to make that distinction because the rational numbers, for example, they are a subset of real numbers, It turns out that any non-empty set of rational numbers, which is bounded above, also has a supremum because all rational numbers are real. However, that supremum is not guaranteed to be a rational number. Okay, that's a fundamental thing to know. So it's good to emphasize which is also a real number. Singular here. Okay, that is the completeness axiom. There is also a dual concept of a greatest lower bound of a set S which is non-empty and bounded below, also called the inf or infimum of S is the more official name. And that would be an element, a real number that is less than or equal to all elements of S, and also any number greater than it is not a lower bound of S. It's a dual kind of definition. Number 2, define what it means for a sequence. Let's use green here. Sequence xn of real numbers to converge to a real number L. By the way, I go ahead and use this notation for sequences with curly braces around the xn here. It's probably not the best notation. It is the notation that Russell Gordon's book uses. It's a little too reminiscent of set notation. Many books use this notation for a sequence with parentheses, and it's probably better, but I'm going ahead and being consistent with Russell Gordon here. What does it mean for such a sequence to converge? Intuitively, and this is worth thinking about, it means I can make the elements, the terms in the sequence, as close as I like to L by taking n, the subscript here, sufficiently large. How do you make that precise? That's a difficult thing, okay? It took mathematicians hundreds of years to figure it out, and you're learning it here very quickly in your real analysis course. Let's go ahead and write out what it means. This means for all epsilon greater than 0, again, the upside down A means for all, it's the universal quantifier. For any number, positive real number, intuitively you imagine epsilon to be small, but it doesn't have to be small. You just think about it that way intuitively. There exists some large, possibly large number, call it capital N, which is going to be a natural number. This fancy n represents natural numbers, the counting numbers, 1, 2, 3, 4, etc. Such that if little n, the subscript of xn, is greater than or equal to capital N is your measure of sufficiently large, then little xn will be within a distance of epsilon of L, really, really close to L if epsilon is really small. You could write it this way. N greater than or equal to capital N implies that the absolute value of xn minus L, and remember, this is really key, the absolute value of the difference of two real numbers is the distance between them, is less than epsilon. Okay? No matter what epsilon is, no matter how small you might say, there's some natural number, possibly very large, it needs to be sufficiently large, so that if you know the subscript of the xn is greater than or equal to that possibly very large number, capital N, then the value of x sub n, the term in the sequence, is within a distance of epsilon of L. On a number line, if L's right here, and this distance is epsilon, and this distance is epsilon, this would be L plus epsilon, this would be L minus epsilon on a number line. Eventually, the sequence terms are going to get inside this interval and stay inside the interval. Okay? Another way to say this is you can write the distance between xn and L is less than epsilon for all little n greater than or equal to capital N. That's okay as well. Number 3 is essentially the negation of the previous definition. Let xn be a sequence of real numbers and let L be a real number. In number 2, we defined what it means for the sequence to converge to L. What does it mean for the sequence to not converge to L? We need to negate this definition. Okay, so again, this definition intuitively said, no matter how close, no matter how small epsilon is, what kind of tolerance I have, the sequence will eventually get inside there. What would the negation of that be? Think about it intuitively. I mean, you can make this precise, but I think it is helpful to think about it intuitively. There is some possibly very small epsilon, so the sequence ultimately doesn't stay inside here. How do you say that precisely? Let's go ahead and write that out. There exists an epsilon. Change the for all to there exists, satisfying the same condition that it's positive, such that we need to change the exist here to a for all. For all capital N and N, no matter how large, there is some L and little n greater than or equal to capital N. Think about negating this part. It still needs to satisfy the same condition that it's greater than or equal to capital N, such that the opposite of this is true. Xn is not within epsilon of L. The distance between Xn and L is greater than or equal to epsilon. Okay? These are the traditional ways of writing the answers to 2 and 3, with, in particular, a greater than or equal to there, a less than there, and a greater than or equal to there. Those are a little bit arbitrary. This could have been a strict greater than there, for example. This could have been a less than or equal to. And if that were a less than or equal to, I want to negate it with a strict greater than. It's not a real big deal. This is more traditional, though. Okay? That's what it means for the sequence to not converge to L, the particular number L. It might converge to some other number, or it might not converge at all. But in either case, if it does not converge to L, then you can say this is true. And this is how you would prove it does not converge to L. The definitions, these precise definitions, are useful for doing proofs. Number 4, define what it means for a sequence Xn of real numbers to be, don't say Cauchy, say Cauchy. Cauchy sequence. Cauchy sequence, okay? With a sequence converging to a real number L, the terms in the sequence eventually get really close to L. With a Cauchy sequence, we don't assume that. We don't assume they get close to some number L. We assume the terms eventually all get close to each other. For all epsilon greater than 0, no matter how small, there exists some possibly very, very large number capital N, so that all the terms after the subscript capital N are within epsilon of each other, are close to each other, because again, you're imagining epsilon to be small. For all epsilon that are positive, there exists some capital N in the natural numbers, such that M and N both being greater than or equal to capital N implies the distance between Xm and Xn is less than epsilon. Okay? Another way to write this would be the distance between Xm and Xn is less than or equal to epsilon for all little m and little n greater than or equal to capital N. Is little m greater than little n? Not necessarily, okay? Could be the other way around, or they could even be equal in the trivial case, and this would be 0 if m and n were equal. So with the convergence to a number, the terms again are getting close to that particular number. With Cauchy sequence, the terms are getting close to each other. You might wonder, are these equivalent concepts? And the answer is, well, at least in the real numbers, they are. There's something called the Cauchy convergence criterion. It's an if and only if statement. It's a theorem statement. It says a sequence of real numbers Xn converges to some number L. I'm not going to bother writing that down. I'm just saying it converges, but that would mean it does converge to some number L. If and only if, which you can abbreviate IFF, Xn is a Cauchy sequence. That's a theorem. It needs to be proved. I'm not going to prove it. One direction of the if and only if is not too hard to prove. The direction that's not too hard to prove is the forward direction here. If xn converges, then it's a Cauchy sequence. If the xn terms get closer and closer, arbitrarily close to some number L, when n is sufficiently large, then the terms are going to get close to each other. That proof's not on this test, but it's something you should be able to do that direction, and I will tell you the triangle inequality is needed. We will use the triangle inequality later in this. The other direction, if it's a Cauchy sequence, then it converges to some number L, is a lot harder. You do need the completeness axiom, and you need a lot of ingenuity to figure that out. You should be able to find it in your textbook, though. We're not going to prove that. Number 6 says to state the Bolzano-Weierstrass Theorem in relation to a sequence xn in a closed interval from a to b of real numbers. That's the assumption. There are various ways of stating the Bolzano-Weierstrass Theorem. One way of saying it is that any bounded sequence of real numbers has what's called a convergent subsequence. You can also state it in terms of n-dimensional space, Rn, where the elements are n tuples of real numbers. You can say that any bounded sequence in Rn has a subsequence which converges. Going to be a little bit more precise in what we're saying here. It also comes up in Russell Gordon's book this way. And say the interval that bounds the sequence is from a to b, and we're also going to say the convergent subsequence converges to something in this interval. So it's a little bit more specific, you might say. Let's go ahead and write that out. If xn is a sequence in this closed interval, closed and bounded interval from a to b, including the endpoints, I'll just do a parenthetical remark here. So xn is bounded both above and below, then there exists a subsequence. I haven't defined what subsequence is. We'll talk about it intuitively here in a minute. X sub p sub n, say, of xn, which converges to some number, some real number in this closed interval from a to b. Okay, xn itself may not converge, but it's got some subsequence that converges. What is a subsequence? I'm not going to give a rigorous definition here, but just think intuitively. If your original sequence consists of, if you list out the terms x1, x2, x3, x4, x5, etc., a subsequence is a subset, you might say, of this, except you want to emphasize that the terms come in the same order. And even calling it a subset is misleading in another way, in that the terms actually can repeat, and you want to think of them as separate terms, whereas with sets, if something repeats itself, you don't think of that as adding anything to the set. Intuitively, a subsequence might be, for example, x2, x3, x5, x7, x11. Notice I'm picking my subscripts in a special way here to be prime numbers here. That's arbitrary, but that would be an example of a subsequence. P sub 1 would be 2, P sub 2 would be 3, P sub 3 would be 5, P sub 4 would be 7, P sub 5 would be 11 for this particular example. Now we've got some true-false questions. Number 7, between any two distinct real numbers, there is a rational number and an irrational number. That is true. Okay. The more official way to say this is the rational numbers are dense in the real numbers, and the set of irrational numbers is also dense in the real numbers, but you don't have to say it that way. In fact, it would also be true if we said between any two distinct real numbers, there are infinitely many rational numbers and infinitely many irrational numbers. Okay, that would also be true. The set of such rational numbers between any two real numbers would be an example of what's called a countable set. And the set of irrational numbers between any two distinct real numbers would be an example of something called an uncountable set. I'm not going to define those terms. I'm not really going to emphasize countable and uncountable. except right now in this problem and number 8 and number 9, other than to say uncountable sets and countably infinite sets are both infinite sets, but somehow uncountably infinite sets are bigger, a bigger size of infinity, and that's something you should learn about in your class, but I'm not really emphasizing it besides some true-false questions here. And number 8 says the ordered field of rational numbers Q is uncountable. Q stands for the rational numbers, Q for quotient. That you should know is a false statement. It's countable, okay? It's a smaller size of infinity than the irrationals. If this was the irrationals being uncountable, it would be true. Again, I'm not really going to go into depth about that. I'm not going to go into depth about number 9 either, other than just to say that this is true. If you're learning about cardinal numbers, given any set S, its power set, which consists of all subsets of S, has a strictly larger cardinality size, you might say. This is certainly true when S is a finite set. In fact, if S has n elements, it turns out its power set has 2 to the n elements. But it also turns out to be true in terms of the cardinality with infinite sets. Again, I'm not getting into details, but this is a fact that I test my students about, just to know that's true when we talk about it. Getting back to more strictly real analysis topic here, number 10 says the Archimedean property can be proved just based on the ordered field axioms. What is the Archimedean property? I will give some detail about that. Of the real numbers, it says, given any two, say, positive real numbers, a comma b and r, and just to keep it simple, a is positive and b is positive. You can get away with one of these being negative, but I'm just going to emphasize the simpler case. Then there exists a natural number, n, such that n times a is greater than b, and this would be trivial if b were negative. A could be really small, for example. B could be really large. There's some natural multiple of A that is bigger than B. Can this be proved just based on ordered field axioms, meaning you've got a set that is both a field, an algebraic field, and an ordered field that's got an ordering that respects the field properties? That turns out to be false. And when I teach this course, I do emphasize that by emphasizing there are some non-Archimedean ordered fields. Okay, there are fields that are also ordered fields that do not satisfy this property, but R does. So how do you prove it for R? You end up actually needing the completeness axiom. Even though the n here, for example, doesn't have to be a real number, or doesn't have to be it can be taken to be a natural number is what I'm trying to say. This is also equivalent to saying the natural numbers are not bounded above. Seems a little strange that you need the completeness axiom to prove it. You actually can get away with other axioms, but you do need some other axiom besides just the ordered field axioms. Okay, so true, so far with true, false, 7, 8, 9, 10, 11, true, false, true, false. Okay. Number 11 is our last true, false. The set of all real numbers that are limits of subsequences of this particular sequence, the values of sine of n, in other words, sine of 1, then sine of 2, then sine of 3, it would be assumed n is in radians here, consists of the entire interval from -1 to 1. As a set of outputs of a sequence, this is actually a countable set. However, this is an uncountable set. So because of that, you might think the answer is false, but I actually teach my students the answer is actually true. Every real number in this closed interval, which is an uncountable set, is a limit of some subsequence of this. That's pretty amazing, okay? Even though that's, as a set, a countable set. I don't prove it. It's kind of hard to prove, but it is true. For any real number in here, whether rational or irrational, there's some subsequence of this that converges to it. If you graph the values of sine of n for various values of n, you will see that they kind of densely fill in the interval, or the interval from -1 to 1, which makes it a little bit more plausible that this might be true, but it actually is true. Number 12 says, state the limit superior, limsup, and limit inferior, liminf, of this sequence defined by this formula. No reasons need to be given. Okay, what is a limsup and a liminf? I'm not going to define them here. Instead, I'll think about it intuitively in terms of a theorem. In general, your sequence xn may converge or may not converge. If it doesn't converge, but it's bounded, we know by Bolzano-Weierstrass that it will have a convergent subsequence, and possibly more than one convergent subsequence. In fact, like this one, possibly even uncountably many convergent subsequences. The limsup turns out, based on the definition of limsup, which I'm not stating, and a theorem, is the sup of all subsequential limits, of the set of all subsequential limits. And the liminf is the inf of a set of all subsequential limits. This sequence here, defined in this piecewise way, I mean, you can figure out the terms. For example, x1 is, plug in n equals 1 up here, get 5, minus 1 is 4, x2 would be this case, plug in n equals 2 there, get negative 2. If n is 2 there, you'll get plus 1/2 is negative 3/2, etc. You could go ahead and figure out those numbers, but I hope it's pretty clear looking at these formulas here that the terms of the sequence sort of get closer and closer to 3 different numbers, 5, negative 2, and 8. On a number line, you could try plotting these things, negative 2, 5, and 8, and you'd see that they're clustering near those numbers as n continues to get higher and higher, but bouncing back and forth because of the piecewise nature. What that means, I hope it's intuitive, that the set of all possible subsequential limits consists of 3 numbers. S equals negative 2, 5, and 8 is the set of all subsequential limits. A little bit more precisely, the set of all numbers such that there is some subsequence of this that converges to those numbers. It's a 3-element set. Its sup and inf are its biggest and smallest members. Therefore, limsup of xn as n goes to infinity, sometimes written in a shorthand with a lim sign and a vertical line above it, is the sup of s. It's a 3-element set. Its sup is its biggest element, its maximum, which is 8. And the liminf of xn, sometimes written with a line below the limit sign, is the inf of s. And that's the smallest member here of this finite set, negative 2. Okay, that's the intuition. So what I do is intuition with the first exam about this stuff. With the second exam, there might be a proof or two related to the definitions of limsup and liminf. Back with example 11 here, or problem 11 here, actually, that's good to think about as well. The limsup of this set, of this sequence, excuse me, is actually positive 1, and the limsup of this sequence is or the liminf of the sequence is negative 1. Limsup is 1, liminf is negative 1. And this interval is S, the set of all subsequential limits. All right, we're on to the proofs now. Though one of these proofs does involve doing some calculations. For sake of time, I'm going to more outline the proofs. I do teach my students to write proofs in sentences, but we're already 30 minutes into the video here. And I've got essentially 6 of these problems I want to do. It might get too long if I do them all in detail. So I'm going to give essentially outlines of proofs instead of full proofs. And for exams, I'm a little bit more flexible with that with my students anyway. All right, first one. Let A and B be real numbers with A less than B, and let S be this open interval, right? That's notation for the open interval, the set of all x in the real numbers with a property that x is strictly between A and B. Open interval. Prove that the supremum of S is the right endpoint B, even though B is not part of the set S. If I had chosen the closed interval from A to B here, and that would mean using less than or equal to's here and here, the sup would actually still be the same number, b. So what this illustrates, without getting into details, is that a sup, or an inf, of a set that's, say, bounded, like this set is, might be in the set and they might not be in the set. That's a fundamental thing to know. But in either case, we're proving the sup is this particular number. So what do I need to do? I need to go back to the definition of the sup, which was the very first problem on the sample test. Let's look at it again quick. It's an upper bound of S. Given an arbitrary element of S, it's going to be less than or equal to beta. And it's the least upper bound of S. Anything less than the sup is not going to be an upper bound of S. There'll be something in S bigger than it. We need to prove that where the beta is this b, which is the right endpoint of this interval, and it's not in the set. Well, showing it's an upper bound is essentially trivial by definition. Since by definition of this set from A to B, this open interval from A to B, since this is true, it's by definition the set of all numbers strictly between A and B. That means given x in S, by definition, x is less than beta, or b. So x is also less than or equal to b. Okay? It's even a little bit more than I probably needed to write. Okay? It's obvious. Therefore, b is an upper bound of S. I guess I'm starting to write sentences here. What about being the least upper bound of S? Let alpha be less than b. I need to show alpha is not an upper bound of S, and then I'll be done. Well, certainly if alpha is less than a, it won't be an upper bound of S. If alpha is less than a, in fact, you could say less than or equal to a, then, for example, alpha is less than a plus b over 2, the average of a and b, which is in S. Now, technically, you might say we need to prove it really is in S, that the average of a and b, the midpoint of this open line segment, truly is in S. I'm not going to take the time to do that. This can be proved with the ordered field axioms. Well, I'll give the idea. I mean, essentially, you know, for example, a plus b over 2 is less than b plus b over 2, which is 2b over 2, which is b, and it's greater than a plus a over 2. This is all because a is less than b, which equals a. Okay, that's essentially the proof without being super formal about it. So we found something in S that's greater than alpha. That means alpha is not an upper bound of S. But that's a certain case. What about the other case? If alpha is greater than a, which means really a is less than alpha is less than b, then you'd want to take the average of alpha and b. And that's going to be an element of the set S, this interval, this open interval from A to B, once again because of the same kind of ordered field properties. I could write alpha, let's go ahead and write this kind of thing with alpha in place of A. Alpha equals alpha plus alpha over 2 is going to be less than alpha plus b over 2 is less than b plus b over 2, which is b. So alpha plus b over 2 is an element of S greater than alpha. And that means alpha is not an upper bound of S. We're done. QED. If you don't really know what you're doing, you won't really even know that you're done, even if you wrote these things, okay? You need to realize we are done. We needed to show B is the sup of S. It's an upper bound of S. And it's the least upper bound if you've got something less than B, then that something, that alpha in this case, is no longer an upper bound of B, of S, excuse me. We needed to separate it into cases here. Either case, we found something in S bigger than alpha, and that means we're done. That also means B is the least upper bound of S, the sup of S. Number 14. Let S be a nonempty finite set, and emphasis on the word finite and nonempty, of real numbers. Prove that S contains its supremum, that the supremum of S is an element of S. It's important in this kind of problem to realize it certainly doesn't hurt to go ahead and just write the elements of S in order. WLOG means without loss of generality. We can say S equals x1, x2 through xn. This is not a sequence, this is a set of real numbers. And assume the subscripts give the order. x1 less than x2, less than x3, etc. And there's no harm in assuming these are all distinct. Okay? What's the idea? It's kind of similar to that problem about subsequential limits in limsup and liminf. Finite set, the biggest thing is going to be the sup. The claim here, we claim sup S equals xn. And note, xn is certainly an element of S. If we can prove this claim, we'll be done. Okay? Well, once again, the fact that this thing, xn in this case, is an upper bound of S is trivial. Clearly, x is less than or equal to xn for all x in S, because this x could be x1 or x2 or x3 up through xn itself. So xn is an upper bound, of S. Is the least upper bound? Yeah. I mean, you can draw this on a number line, it should make intuitive sense. If alpha is less than xn, well, that actually does it, because xn is an element of S. This means since xn is in S, alpha is not an upper bound of S. It was almost too easy. Okay? I mean, certainly if alpha happens to be less than x sub n minus 1, for example, you could also use x sub n minus 1 there. It might not be less than x sub n minus 1. It's good enough that it's less than xn, and in fact, that's not only all you need, but you do need that fact because alpha could be between x sub n minus 1 and x sub n. Since x sub n is a part of S, alpha is not an upper bound of S. Okay? Therefore, 3 dots means therefore, we've proven the claim, the sup of S is xn, therefore the sup of S is an element of S. Okay, so finite sets contain their sups and they also contain their infs. Yeah, I guess I'm writing more sentences than I thought I would here, but outlines of arguments are going to be fine wherever I do them here. Number 15 is a bit more computational. Define a sequence xn recursively by this equation. X sub n plus 1 equals in terms of the previous value, 1/3 x sub n plus 6 for, well, starting with n equal to 1 being 0, this equation is true for n equals 1, 2, 3, etc. It's a recursively defined sequence. Part A is just computational. Find x2, x3, and x4. x2, by this formula, when n is 1, 2 is 1 plus 1, is 1/3 times x1 plus 6, so that's 1/3 times 0 plus 6 is 6. x3 is 1/3 times x2 plus 6. 2 plus 6 is 8. And x4 is 1/3 times x3, which is 8, plus 6. That'll be 8 plus 18 all over 3. That'll be 26 over 3, which is 8 and 2/3, 8.6 repeating. Okay, so those numbers are the values of x2, x3, and x4. Part B says, the sequence is bounded above by 9. I'm telling my students that. Would that be difficult to prove? No, it's not too bad. You'd want to use induction, actually, and I'm not requesting that here. The inductive step would use, well, the base step is easy. x1 is 0, which is certainly less than or equal to 9. The inductive step would assume xn is less than or equal to 9 and use this fact to prove that x sub n plus 1 is less than or equal to 9. And that's fairly easy. Since xn is less than or equal to 9, you could say this is less than or equal to 1/3 times 9 plus 6. 3 plus 6 is 9. And you could use then the principle of mathematical induction to verify that that means xn is less than or equal to 9 for all n, not just one n. But my students had to do some algebraic manipulations with the expression xn plus 1 minus xn to confirm that this is always greater than or equal to 0. And that means xn plus 1 is greater than or equal to xn, so the sequence is monotone increasing. You can actually prove part B here. You can verify it without using induction. You might think you need to use induction since you're proving something is true for all natural numbers. It's actually easy enough to avoid that here. It's essentially just a calculation, possibly also using the fact that the sequence is bounded by 9, I think here. xn plus 1 minus xn for an arbitrary natural number n is, by the recursive formula, 1/3 xn plus 6 minus xn. That simplifies to 6 minus 2/3 xn. And since I'm saying go ahead and assume the sequence is bounded above by 9, that means if you subtract 2/3 times the sequence here, this is going to be greater than or equal to 6 minus 2/3 times 9. 6 minus 6, which is 0. And we're done. We don't really need induction there because we didn't need to use an inductive hypothesis. It's obviously true based on this assumption being true, which can be proved with induction just by calculation like this. You don't have to use induction. If you can avoid induction, as we can here in part B, then do avoid it. You don't need it. Sometimes you need it, though. This time we didn't. So the sequence is monotone increasing. And part C says, since the sequence is monotone increasing and bounded above, it converges to some limit L. That's a fundamental theorem in real analysis, is that a bounded monotone sequence converges, whether it's monotone increasing or monotone, well, if it's bounded, it doesn't matter if it's monotone increasing or decreasing. You can also say a monotone increasing sequence that's bounded above converges, and a monotone decreasing sequence that's bounded below converges. Those are other things you can say as well. It converges to some limit L. By letting n go to infinity in this equation, find the value of L. Okay, so we take the limit as n goes to infinity, and the limit as n goes to infinity of xn plus 1 and the limit as n goes to infinity of xn are going to be the same thing, because they're sequences essentially that are just shifted from each other. by algebraic properties of sequences, of limits of sequences, I can write this thing on the right side as being 1/3 times the limit as n goes to infinity of xn plus 6. And then I can replace these limits with L. They are both equal to L, including this one. So L is 1/3 L plus 6. And I hope you could have predicted the answer ahead of time. This means 2/3 L equals 6. So L is 6 times 3/2 is 9. Yeah, the limit, as you should have guessed, is 9. Drink of water here. Suppose An is a sequence of real numbers converging to L1 and Bn is a sequence of real numbers converging to L2. Prove that the sequence whose terms are the sums of the terms of these sequences converges to L1 plus L2, just what you would guess. It's good to do scratch work on this kind of problem ahead of time. This is sometimes what's referred to it as an epsilon over 2 proof. I won't say what that means right away here. Intuitively, we're trying to make the distance between An plus Bn and L1 plus L2 as small as we like by letting n be sufficiently large. Just going back to like problem number 2 here. We're trying to verify this kind of thing, where our sequence xn is An plus Bn. For newcomers to this stuff, this is definitely not clear what to do here. Hopefully you've been taught enough to realize we should rearrange a little bit. We should associate the An with the L1 and the Bn with the L2, and then use the triangle inequality to say the absolute value of this, the sum of these two things, is less than or equal to the sum of their individual absolute values. Like that. And intuitively, you're saying to yourself in your mind, okay, I can make this small and this small by letting n be sufficiently large. Though the measure of sufficiently large could be different. So how do you deal with those kind of subtleties? We want this to be ultimately all less than epsilon, which can happen if, say, this first one's less than epsilon over 2 and the second one is less than epsilon over 2. When n is sufficiently large, if n is sufficiently large. Again, how large is sufficiently large? You've got to be sufficiently large for both of these things to be true. If there's an n for this one and another n for this one, taking the larger of those two capital N's will do it. Okay, so that's initial thinking about how to go about doing this here. If you're watching this video, you've probably done this similar kind of problem already. Let's look at the proof now. Start by saying let epsilon greater than 0 be given. For my students, I say that's like a stamp. Put it on these kinds of proofs right away. We need to choose two capital N's. One for the An's in L1, one for the Bn's in L2. Choose, call it, say, capital N1 and capital N2 that are both natural numbers, and one could be much bigger than the other for all you know, such that little n greater than or equal to capital N1 implies the distance between An and L1 is less than, don't pick epsilon, but pick epsilon over 2. We're trying to get to an epsilon at the end. You might wonder, do you really need to do that? And I'll say you don't, but it's best to do it this way. You could have epsilon here and on the next line and a 2 epsilon there, and it still would be a logically valid proof. And n greater than or equal to n2 implies that Bn is within epsilon over 2 of L2. Then, by the triangle inequality, which should be mentioned at first in this course, if little n is greater than or equal to capital N, defined to be the bigger of the two, the maximum of n1 and n2, then it's bigger than both of them, I can say both of these inequalities are true, and now I can do this kind of scratch work. I'll redo it over here. The distance between an plus bn and L1 plus L2. The first equality here is just algebra, rearranging. You could say the commutative property and the associative property if you want to be a little bit more picky about it. The triangle inequality is right there. And then using the fact that little n is bigger than both capital N1 and capital N2, and using these lines, says this is less than epsilon over 2 plus epsilon over 2, which is epsilon, and that means we're done. For all epsilon greater than 0, we found a capital N, so that if little n is greater than or equal to capital N, then this distance is less than epsilon. The exact same idea as we had in number 2, just with more subtleties based on the fact that we got these two sequences here. And that means we're done. QED. Yeah, writing more sentences here. Not really in the previous problem. Last page. Two more problems. 17 says, prove that a monotone decreasing sequence that is bounded below converges. There's a theorem that a monotone increasing sequence that is bounded above converges. In fact, that's what we were talking about in number 15 with the recursive sequence. Right here. It's a theorem, really, in the textbook I use, Russell Gordon's text. There's no theorem that says a monotone decreasing sequence that's bounded below converges, but it really is a theorem still, proving it's the same level of difficulty. And it's based on the completeness axiom. You may assume it is true as essentially equivalent to the completeness axiom that a non-empty set of real numbers which is bounded below has an infimum. The completeness axiom, coming back there again. Every non-empty set of real numbers which is bounded above has a supremum in the real numbers. That turns out to be equivalent to saying every non-empty set of real numbers that is bounded below has an infimum in the real numbers. That's the assumption here. We're going to need that. Okay? Let's do our scratch work by just drawing a picture and thinking here. Got our sequence xn. Maybe x1 is here. It's a monotone decreasing sequence. Maybe x2 is there. x3 is there. Maybe x4 equals x5. That's possible. Still going to be monotone decreasing. x6, etc. And these are bounded below. There's some lower bound, maybe a little m down there, that they never get past. We want to show this sequence converges. Since it's bounded below as a set, it's going to have an infimum, an inf, that may or may not be in the set, but it will have an inf. The inf is the greatest lower bound of the set. It has got to be the inf that is what the sequence is approaching. Anything bigger than the inf is not going to be a lower bound of the set. There'll be something in the set below it. And that's true no matter how close that bigger number is to the inf. And when I say how close, I mean arbitrarily close, like within epsilon. Seeing what to do here? It is a convergence proof, so I need to start by saying let epsilon greater than 0 be given. What should I use for my number bigger than the inf? Let's say alpha is the inf of the set of all outputs of the sequence, the set of all xn as n ranges over the natural numbers. This is representing a set, not the sequence itself, the outputs of the sequence, not the terms of the sequence. They're defined by the terms of the sequence. But this is just a collection here, and this is its inf. How about alpha plus epsilon? Is my number bigger than alpha? Bigger than the greatest lower bound. So it won't be a lower bound. Since alpha plus epsilon is bigger than alpha, the inf of this set, it's not a lower bound of the set. What do I need to do? I need to find a capital N. So if little n is greater than or equal to capital N, x sub little n is within epsilon of alpha, if I'm trying to prove alpha is the limit, which is what I'm trying to do. Certainly, x sub capital N would we want to be within alpha. And since the sequence is monotone decreasing, if little n is greater than or equal to that capital N, it should those xn should also be within epsilon of alpha. It's not a lower bound, so there exists, go ahead and call it capital N, a natural number capital N such that I could write alpha is less than or equal to x sub capital N is less than alpha plus epsilon, because alpha plus epsilon is not a lower bound of this set. That's what it means to not be a lower bound of the set. There's something in the set less than alpha plus epsilon. And it's got to be less than or equal to alpha, because alpha is a lower bound of the set. Since this is monotone decreasing, we can say something a little bit more. We can say alpha is less than or equal to little x sub little n is less than or equal to little x sub capital N less than alpha plus epsilon for all little n greater than or equal to capital N, because it's monotone decreasing. X sub capital N plus 1 would satisfy this, x sub capital N plus 2 would satisfy this, etc. But this means that the distance between xn and alpha is less than epsilon for all little n greater than or equal to capital N, and that does it. That means, therefore, the sequence converges to alpha. Okay, not an easy proof, a little tricky, but not super hard either. Definitely something you want to practice. All right, this is the last problem. Prove that this sequence is a Cauchy sequence. Probably need some scratch work here too. This one's kind of subtle, tricky as well. We're trying to show that the distance between xm and xn can be made as small as we like if both little m and little n are sufficiently large. Go back to number 4. No matter how small epsilon is, there's some capital N, so that if both of those are bigger than or equal to capital N, this is true. We're using this particular sequence. The only thing it seems reasonable to try here is to just see if you can simplify this thing. This is scratch work. I guess that means we need a common denominator here of the product of these two things. 4m plus 3 and 4n plus 3. For the 8m, I've got to multiply by 4n plus 3. And for the 8n, I need to multiply by 4m plus 3. It's going to give me 32mn plus 24m minus 32n mn minus 24n. I'm not going to bother to multiply out the bottom. It does simplify. The 32 mn's cancel. 24m minus 24n, the 24 can be factored out. And it can even, since it's positive, it can even factor it out in front. And I can also put the absolute value signs up top, say, and not necessarily on the bottom, because the bottom's already positive. I mean, I could put absolute value signs around it, but I don't have to. M and N are positive here. And so, kind of complicated still. Simplify. How? This is the trickiest part. Without loss of generality, we can get rid of that absolute value sign by assuming, say, m is greater than or equal to n. And in fact, we can simplify even more if we allow inequalities here. I mean, we're trying to ultimately say this is less than epsilon if m and n are sufficiently large. Why don't we just use some inequalities to simplify this? Less than 24. M and n are both positive, so if I replace m minus n with just m, that's okay as long as I have a less than sign. It's not equal, but I can put a less than sign. And also, I could make the fraction bigger by getting rid of the plus 3's in both of those. 4m times 4n. The m's cancel. The 24 divided by 4 times 4 is 16. 24 divided by 16 is 3 halves. I can write this as 3 over 2n, it looks like. I want that to be less than epsilon. That'll be equivalent to choosing, if you solve the inequality for n to be greater than 3 over 2 epsilon. I divided both sides by epsilon, multiplied both sides by n, and switched the order of where things were. Now you want your capital N in your proof to technically be a natural number, though it's really not a big deal if it's not. But just to be sort of official, we should probably say let capital N be some integer greater than this, which you can do by the Archimedean property, actually. So here's the proof. Do your stamp at the beginning, let epsilon greater than 0 be given. Choose capital N in the natural numbers so large that it's bigger than 3 over 2 epsilon. It's really essentially the Archimedean property. Well, the integers are not bounded above, and yeah. This is not going to be an upper bound for the integers. There's some integer greater than that. Archimedean property. If you want to be a bit more specific, you could say let n be the ceiling function applied to this thing. You could put the symbol for the ceiling function if you like, to emphasize n as an integer. Then, if both little m and little n are greater than or equal to capital N, and go ahead and mention your without loss of generality here. Then we can say all this stuff. And to save time, at the end of this video, I'm just going to do this. And oh, don't circle the want though. Put all this stuff here, blah, 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 and then say, that's less than or equal to, if I get to this point, 3 over 2 times capital N, which, since I've chosen capital N like this, that's going to allow me to say that's less than epsilon, right? I can get from here to here by dividing both sides by capital N and multiplying both sides by epsilon and switching the order around. Everything's positive, so there's no problems with inequalities switching direction unless you purposely switch direction, and which is what I did there. I mean, you know, 4 being less than 5 is equivalent to 5 being greater than 4. So that's not saying anything different. So I didn't multiply by a negative number and have to switch the inequality because of that. I just decided to put things on different sides. Okay? And that is the end of that proof. That means it's a Cauchy sequence. It also means it would converge. And if you wanted to know what it converges to, it would converge to 8 over 4, which is 2 if you're interested. And that's the end of this video. Thanks for watching.